Hey, welcome back to Science. The last time we were actually in class, we had been working on a lab. Specifically, in case you forgot, the question I had posed to you was, what relationship, if any, exists between the mass of a substance, in our case we were using water, the amount of time that object spent on, or that water spent on a hot plate, which essentially is saying, hey, the amount of thermal energy added, and the change in temperature that substance was going to undergo. Now in doing this, we realized we had two basic ways we could do this. For one thing, with three variables, we had to control one of them because you can only test two at a time. We're going to manipulate one, that will be called the independent variable, and then the other thing will be called the dependent variable. So that meant that we had to keep one of these constant each time. I gave you a couple different options. You gave me a couple different options. One of them was to have the change in temperature be the same every time. Then you'd see how differing masses, what effect the differing mass had on the amount of time it took to go through that change in temperature. The other option was to put the water on the hot plate for the same amount of time every single trial and see what change in temperature happened. Choice was yours. Method was totally up to you. There are a lot of ways to do this that were good. There are a lot of ways that were bad. We had a lot of errors. Some of you broke glass. You know who you are. Whatever. We learned a lot. There were a ton of errors. That's totally fine. I was expecting that. It's a learning experience. Honestly, it was a learning experience for me too, because I learned some of the things that can help you not break glass, or help my students not break glass in future years. For now, let's take a look at some of the things that we learned. Okay, in doing this lab, most groups, for whatever reason, chose to control the amount of time. So as an example, this group kept their water on the hot plate for 90 seconds every time. Totally fair. I like on here, they also, oh, this one didn't. They should have probably told us what temperature or what setting they had the hot plate on. That alone was some of the error that some of you guys had. We'll get to that in a second. The data looked like this. They put in that for their best fit line. Do you remember what the issue would be with that as the best fit line for this data? There is an issue. Stop this right now. Try to recall that for yourself, or think it through for yourself. What would be the problem with that? Okay, did you figure it out? Problem with this would be that if you continued this green best fit, it would mean that at some point you'd have enough mass that you can put the water on the hot plate for 90 seconds and the temperature would not change. But wait, it gets better. If you put even more mass than that on the hot plate, you can have it sitting there for 90 seconds and the temperature of that water on the hot plate would actually go down. Does that make sense? Of course not. So this is a good try. Thankfully, the students that came up with this recognize that there's that flaw in it. Let's look at another one. So these guys did the same lab. They used a hot plate setting of 8. They left it on for 2 minutes. And they thought that the data would look something like this. That shape, by the way, is called a hyperbola. You'll cover it in math classes if you have not yet. Main thing to know about this is this graph will never hit either axis. And when you think about that, hopefully that makes sense. There should not be any amount of time or excuse me, there should not be any amount of mass that when you put it on a hot plate, the temperature does not really go up. It'll get incredibly close. If we were to somehow have put Lake Superior on a hot plate for 2 minutes, I'm not sure we'd have been able to measure a change in the temperature. Would have gone up, but not by a measurable amount. So this will drop and get very, very close to zero. Theoretically, it will never actually hit zero. As I said, most of the groups chose this particular method for testing. Let's take a look at the other way. Here's a group that chose to control for the change in temperature. So they had a change in temperature every time of 10 degrees Celsius. And their graph, now they identified an outlier here. They know this was tough. Again, there were lots of sources of error in this lab. They identified that, but they thought that this was the most reasonable shape to the graph. And it fits. Why does this make sense? Ask that for yourself right now. Pause the video, answer that for yourself. Awesome. Did you do it? Great. So the more mass is going to require a longer period of time to go through that temperature change. It's kind of logical. Say I'm making my oatmeal in the morning that only requires 175 milliliters of water. That doesn't take very long to get up to boiling. Whereas I put a pot of water with 2 liters, 2,000 milliliters, it's going to take a lot longer to boil. It's just kind of logical. If this graph was perfect, if the data was perfect, it would probably look more like this. I totally made this one up, but it's important that we notice the things that are on the axes. We're saying this is measuring mass or volume. If it's water, it's a 1-to-1 relationship from milliliters to grams. To the time spent having thermal energy being added, or essentially the amount of thermal energy added. What does this tell us about our original question? Well, hopefully what you gathered from this is that thermal energy is indeed comprised of temperature as well as the amount of material. In our case, we're talking about the mass of the water. So how much water there is has an effect on how much thermal energy it has trapped in it. There may even be a third thing, but that's not for now. Now, when you were doing this lab, you had a lot of sources of error. To quickly summarize what we spent a bunch of time in class covering, it would have been ideal to have the hot plate set at the same temperature, same setting the entire time. I found out that if you have it at too low of a setting, the heating element actually cycles. It's on and it's off, so that would mess it up. So something that I should probably have suggested is start at a higher setting. But you certainly don't want to turn the hot plate off each time. In fact, ideally, you'd have the hot plate been on for a good amount of time so that it's up to that high temperature. And then we can put the water on. In fact, it's even better. The way that I've seen some students do this is they put their water on, take a stretch, they're watching the temperature. They don't start the clock until the water gets to a set temperature. For example, 30 degrees Celsius. Then, from that point on, they can measure for the amount of time they wanted or for the temperature change they were looking for. What are some of the advantages to this compared to how you did that? Pause now. Okay, so the advantages are we're controlling more of our variables. And we're also taking into account that the beaker needs to spend a little bit of time warming up. That last graph that I showed you had a y-intercept. I think that y-intercept actually is real. You'd think that it would be 0, but it's not just the water on the hot plate. It's a beaker. That didn't change each time. At least it wasn't supposed to be changing each time. Sources of air, anyone? Was not supposed to be changing. But that is going to take a little bit of energy to change its temperature as well. So that's why you actually should have had a very small y-intercept if you did this type of a graph. What were some of the other sources of air? I'm brain farting right now. Look back in your own notes, see what you can come up with. Again, there were lots of them. That's okay. It was meant to be a learning experience. Did you learn anything?